The final talk for tonight, we have Time Trial, Racing Towards Practical Remote Timing Attacks with Daniel Mayer and Joel Sandin. So please welcome them to the Toorcon stage.
Thanks for coming, everyone. I know it's the last talk, so we appreciate you sticking around to listen to our talk. So this will be about Time Trial, a tool which will help you to race towards practical timing attacks. I'm Daniel Mayer, and I give this talk together with Joel Sandin over here, we're both security consultants with Matasano Security. Matasano is an application security consultancy. We're based out of New York, but we have offices in Chicago and Sunnyvale as well. And we're part of the larger NCC group, which includes ISAC Partners, Intrepidus, and a few other US consultancies. So just a brief overview of what we'll be talking about. First, I'll introduce what are timing side channels, and then we'll talk about how you can actually exploit those remotely and what the challenges are when you do this. Next, we talk about our tool called Time Trial, and we'll show you how you can use that to actually test your own software for timing side channels and see whether they're exploitable or not. And then we put that into perspective, what does that mean for your applications in practice? So we kind of have timing measurements, and then we show you how that relates to certain application functions and what could be exploitable and what is not. So the goal of this is that you hopefully afterwards will have an understanding on what timing attacks are and whether they're exploitable, if it is feasible, or if they're more like theoretical attacks in certain scenarios. Just trying to give you an overview of this and an update on the state of the art. So timing attacks are a type of side channels. So what is a side channel attack? So if you look at your main web applications or any kind of software, piece of software, and everything seems to be secure from what we understand as secure. There's no common flaws which you're aware of in the main way you interact with the application. There may still be ways how you can get information through side channels. Think about it as a web application which doesn't have any kind of cross-site scripting, SQL injection flaws, remote code execution flaws, but you can still get around it to learn something about some secret of the application through other means. But unfortunately, they're not really that smooth as this bypass looked like. It's more of a rocky road, and it's really tough to exploit those kind of things. As you will see, there's a lot of things that can go wrong, and if you make a wrong decision at some point, you may just completely go off trail there. So besides side channels and timing attacks, which we will be talking about, there's a lot of other categories of side channels which are out there. One of them are power consumption attacks, which actually my colleagues Alex and Timur were talking about yesterday in the seminars. And they use power traces from how much power a microcontroller or a system consumes to relate that to data or to secret keys inside of the system. Other options there are radio frequency emissions, sound, the processing time, which we will be talking about. And what all of that has in common is that they are something we can measure on a system which is somewhat related to a secret or some data which the system is processing. So in our setting for time, depending on what data is being used or what the system does, it may take a longer or a shorter time to respond to a certain input. So if you compare this to regular vulnerabilities, cross-site scripting, buffer overflows, things like that, which we know. These are really well understood, and we have a pretty good grasp on how they come about and how to prevent them. There are frameworks now which make it much less likely to introduce those in software. But if we contrast this with side channels, they're much less understood. We kind of know what they are, and people theoretically know what could be a timing side channel, but we don't really know how to look for them effectively, and especially it's really hard to prevent them. We have to go out of our way to prevent them. So we hope to help move from the second part a little bit closer to the first part there. So timing side channels in general are exploiting the fact that response time differs depending on which computation a system performs. So depending on which input you're sending it may take a different amount of time to respond. And that time may also depend on a certain internal system state which you may want to learn about. So for example, if some sensitive credential is involved or like a secret internal system state, we can learn about that by measuring timing from the outside. And they're really easy to introduce, as we will see along the talk. The main question we try to answer, though, is are these things exploitable remotely? Some of these attacks we will see will not be able to do that, and for others, it's definitely possible. So let's dig a bit deeper here and show you a basic example of a side channel. This is that's the Ruby Sinatra application, which has like a post login endpoint up here, and it takes a username and a password. The first thing here is the application checks whether the username it received is valid, and if it is not, then it will reject this request up here. But if the username is valid, it will continue and process the password. And if the password is invalid, it will reject it with also a generic error message down here, or grant the access. So from an application standpoint, you can't really learn something about it because it will return the same message for username or password are wrong. But let's look about the timing for this. If you look at this as like a timeline going from up down, we have the attacker on one side and the target on the other. And the attacker starts its clock and posts the username and the password. And the server will first verify the username, and if it's wrong, it will return here, and we would have a time t0. But if the username was correct, it will continue and do some additional processing down here, and only then return. So the goal here is if we can distinguish this time t0, which would correspond to an invalid user, from a time t1, which is a valid user, then we can exploit this to enumerate valid users in this application. So that's just the basic idea of what a timing side channel is, that we can infer something about the system based on the response times. And we are not the first people, obviously, who are talking about this. This comes mostly out of the crypto community originally. The work by Kocher here was on RSA and Diffie-Hellman, and they were showing how there are timing attacks possible on these kind of systems. And the first remote attacks were done by Bromley and Benet on OpenSSL. And then more recently, there's empirical works which we're building on a lot, which are by Crosby et al. And Nate Lawson and Nelson. They gave a talk at Black Hat in 2010. And our ideas are kind of building on what they started and updating it with more recent results and showing you a little bit more the application side of things. And with this, I'm handing off to Joel, who will be talking about how to exploit these things. There's going to be a little bit of theory in here, so bear with us. It's only a few slides.
Thanks, Daniel. Can you guys hear me okay? All right. Yeah, so let's talk about remote timing attacks and some of the challenges that are involved. When we're performing a local attack against a system, we can measure the execution time directly, and we don't have to account for a lot of external influences when we do the analysis. When we're mounting a remote timing attack, we're not able to measure the execution time directly. We have to deal with network jitter. So what we're interested in is the execution time, which is the signal here. But what we're getting is actually that signal, and added to it is this random propagation time that's caused by the network. And that's what actually gives us our measurements. And it's important to understand when we're performing these attacks, we're not trying to derive the execution time from our set of measurements. We're not interested in the exact execution time on the server. What we want to be able to do is, given two requests, understand if the server took different amounts of time to process those requests. And if we can do that, we can actually do a lot. We may know that the server did an additional database query as part of processing one request versus the other, or the server may have looked at additional bytes of a password that we sent and compared it to some sensitive credential. So that's really the key to performing these kind of attacks over a network in practice. But it isn't easy. So let's look at what these measurements look like in a real system. So here we have a set of samples that we got interacting with a cloud-hosted DigitalOcean instance. And what we've done here is we've plotted the round-trip time, which includes the execution time. This is on the x-axis, and on the y-axis we have how many times we saw that particular measurement. And a couple of things kind of jump out at us right away when we look at this plot. Most of the measurements are skewed towards lower response times, but there is this long tail of higher response times that are much less frequent. And we see a smooth ramp up on the left side of the graph of among the lowest response times. And we also have two peaks there corresponding to the most frequently occurring response times. And right away we can see we can't model this with like a Gaussian distribution or other parametric distribution, and we're not going to be able to use the statistical tests that we get with those distributions, so we have to come up with another approach. And what we're looking for in these sets of measurements, we're going to interact with the server, take many samples, and we're looking for something that correlates well with the execution time on the target. So if we look all the way, whoops, where's my light? There we go. If we look all the way on the left side here, we have the minimum response time. And that seems like a good candidate. That seems like it would correlate well with execution time because that's the execution time plus the minimum added propagation time on the network. And with enough samples, you'd think that that's a well-behaved quantity. So you can actually plot this minimum response time and see how it behaves as a function of server processing time. So if we look at the red line here in this graph, this is actually the minimum response time taken from many samples for each point on that line as processing time increases. And it looks pretty good. It's increasing as server processing time increases. So that's a good correlation, but it's still a noisy correlation, which is a little bit surprising. If we look at other measurements in that, on the left side of that graph, other low percentiles, which I'll explain in a sec, they actually track much better. They track the server processing time much better. So they might, it's better to focus on those low percentiles when we're coming up with a statistical test. The minimum isn't necessarily a good indicator. And as we saw, because the graph is highly skewed and there's multiple modes, we're not going to be able to use the median either. So what do we do? So there's lots of different techniques, but the best known analytic technique is called the box test. This is the one that's performed best in previous empirical studies. And when we talk about boxes, we're actually talking about percentiles. So if we look here, we have what's called the 6th percentile. And this is the smallest sample that's greater than 6% of the measurements. So when we're talking about the minimum response time, that's actually the 0th percentile. And the maximum response time is the 100th percentile. Another way to look at it is that this line kind of divides the area under that curve so that 6% of that area falls to the left of the line. And when we talk about boxes, we're actually talking about a pair of percentiles that define this box. So here we have samples falling between the 6th and 8th percentile in this sample set. That's a box. And the box test actually uses just 2 parameters for performing this test. So now if we superimpose a second set of measurements, second set of samples that were made using a request that took a little bit longer to process. So here, this is 105 milliseconds. It's a 5 millisecond difference. We see right away that these distributions look different. One is shifted. But if we compare the boxes and where they fall, we compare the intervals of response times that fall within those boxes, they're disjoint and they're well ordered. And the samples corresponding to the longer response time actually fall to the right of the samples for the shorter response time. Another way to look at it is that these boxes don't intersect. And you have to determine these, the parameters for this test empirically, so it's going to depend on the network conditions and what you're looking at. But in practice, generally the low percentiles below 20%, picking boxes in that range performs quite well. So this is the test that's implemented as part of time trial, and you get these visualizations. So hopefully it will help you understand Daniel's discussion about time trial.
Thanks. So why do we need a tool for timing attacks? So we feel that when we looked at software applications as part of our work, which we saw theoretical timing attacks in the source code, we couldn't really communicate if there is actually an exploitable vulnerability here or if there's a threat to somebody's customer data. We just know this is theoretically exploitable, but we didn't really, it's very hard to convince somebody that this is actually an exploitable issue or not. So we hope by having a tool, it allows us to separate like theoretical vulnerabilities from actual real vulnerable instances. And we can also have reframing the debate about these attacks from bring the discussion more to what can be exploited versus which of these flaws should we not really focus on when we see them in a software product. So what time trial is at the moment, it's a framework which allows us to capture very precise timing measurements, and then it allows us to do feasibility studies. And what I mean by that is we can take these measurements and put them into perspective using the box test, which Joel just talked about, and we can show you in a visual way whether we can distinguish these distributions or not. And if you can distinguish them, then we can also we could also theoretically practically exploit them. It would just take a little bit more effort. But if you cannot distinguish them, then that's probably a waste of effort on putting to fixing a flaw, for example. What time trial is not right now is that it's a ready-to-use exploit framework which you just point at a web service and tell it, hey, is there any timing vulnerabilities in here? That's not the goal of it. The goal is more to analyze rather than to exploit at the moment. But of course, you can use the statistics we are using to actually build an attack tool based on that. So our design separates something which we call the sensor or the racer, which is the component that actually measures timing data, from a GUI component. And the reason for this is that we would like to have our measurements to be flexible. So we either want to run them in our local network, or we may want to run them across the internet, or if we have a target which is running on a cloud instance, why don't we just rent an EC2 instance as well and run our timing measurements directly from there, then we are much closer to the target, and we're cutting out a whole lot of jitter. So that's why we separated this racer from the GUI, and having a GUI will still allow us to have a convenient way of analyzing the data and scheduling the experiments. And we also decided to use C++ for the racer so that we can really go down to C code and native code to get really precise timing measurements. So the way this works right now is that we have the GUI application over here, which we can use to schedule the actual timing measurements. And they're put in a Redis queue, which is being used to communicate with the racer. That can be over SSH, for example. And the racer pulls out the data from that queue, runs the test against the target, puts the results back in here, and we can plot them in our GUI. So it's like a very convenient way of doing this and still being quite flexible. So the first thing, I kind of hinted at the answer already, but the thing we thought about was how do we do precise timing measurements? So the goal is to cut out as much jitter as possible. So why not cut out the operating system and everything as well and just go down and get a NIC which has hardware timestamping. Those are available like easily from most major manufacturers. They're quite pricey, but you can get them, and they're used for IDS systems a lot. And we were thinking about getting one of those to then have hardware timestamps in our TCP packets to analyze. But the problem is that if you think about putting something in EC2 or something like that, Amazon will not let you send them your NIC of choice and put them into their environment. So that was not really feasible for us. Similar thing is like using an FPGA, which has a network interface on there and does have FPGA code doing the timestamping or analysis, has kind of the same restrictions. So we ended actually up just using our laptop for local experiments and running Linux on there. And for other experiments which were in the cloud, we just got Linux instances in the cloud, and we could run that basically on a variety of infrastructures. So since we decided for Linux, we did some digging, and what can we do to optimize our timing measurements as much as possible. So first thing we did, we're using the clock at time system call to get the time using the monotonic clock, which is guaranteed to never decrease. Some Linux clocks have adjustments which may actually decrease along the time. The monotonic one is guaranteed to always be increasing. And then we also try to isolate our process as much as possible from the operating system and other processes. On Linux, you can tell the kernel that you want to have two cores to be used in total, for example, if you have a two-core system, and one of them should be isolated. What happens then is that the kernel is running only on one core, and it will only ever schedule processes on that core as well. But you can still explicitly assign your own process to the other core. So by doing that, we have a CPU core which doesn't run anything else but our code, which does the timing measurements. And then we also added real-time priority and disabled frequency scaling to make sure that no other process can talk to ours, can interrupt or preempt our process. And frequency scaling really messes up timing and timers because they have to be scaled, and it's just really messy. So disabling those is definitely a good idea. So with that, I'm going to show you real quick how time trial looks like. A lot of things are happening under the hood, so it's not so easy to actually show you how much effort went into it, but so you're going to see it here. So that's basically the GUI when you start it up. The first thing you want to do is go to the settings tab over here, and what you can do here is you can define your racers. So at the moment I have like an EC2 racer in here, which I used for some tests, and I was earlier just playing around with it. I added the Toorcon racer, but the only thing this is, it just names the queue and it tells it the host name to connect to. So you can add a new one just by pressing this button down here, and yeah, I'm just adding a new. I'm just going to put this here. All right, so that's in here. So if you want to do a new experiment, there's an experiments tab. And experiments are just groupings of test runs. They're just a convenient feature. And then down here you have the various trials. So I have, for example, here an HTTP trial, which uses a correct username and one which uses the wrong username. And if you, I'm just going to edit an existing one, but the dialog for adding a new one is the same. So I have a big dialog here. On the left side, which you can't see probably, it's just better. On the left side you can see just the name and the number of repetitions you would like to use. And then you specify a URL, and you just add a post request or a get request here. This, for example, if you're using burp for something, you can just copy paste it from repeater right in here, and it's going to work. And you can, in the corner down here, you can specify which racer you would like to use for this experiment, which CPU core to use, and if you want to use real-time scheduling or not. And if I now just, if you would just start this, it's going to put in a queue, and that queue, the racer would just pick it up, run the experiment, and when it's done, it will show here an end status. and it will get the results. So I have two prepared results here just to make this a bit quicker. So I'm just use this example we talked about before with the correct and wrong username. So for correct username, we expect that it also performs a password check. So this one should take longer than the other one. So if we plot these and say this is the longer one, zoom in here, this should be the longer trial, and this one, which is the wrong password, is the shorter one. And then I'm going out onto my feasibility analysis tab. I see the distributions plotted down here. They're really coarse right now, so I'm going to add a bit more buckets so it's more smooth. Just like this. So if I zoom in a bit, I guess with the naked eye, it's pretty clear that one distribution is shifted from the other. I don't know if the quality of the projector is good enough. But to illustrate this a bit more, I can, for example, modify this plot and say I want to plot it till, it's going to stretch it a bit out. So there's options to customize the plot, and you can run the box test by just clicking this button up here. This is going to add the two boxes over here, and you see they're distinct. And the system will also tell you automatically the distributions are distinct, and that these two timing differences can be separated using the software. So that's basically the gist of it. So we can run these kind of experiments against an HTTP server, and we can also have like a mock-up setup, which I will talk about later, which we used for our feasibility experiments, which I'm going to talk about in a second. Just switching this. Right. So using the tool, we took some data, and we took data mostly to figure out which timing differences we can distinguish in different networks. So we looked at LANs, we looked at the internet at large, just between the home and cloud providers, and different cloud environments like EC2. And again, the goal here was to figure out for which two times T0 and T1 can we distinguish effectively from these different vantage points. And in order to do this, we used something which Crosby et al. Also used in a similar manner. We wrote a little mock-up server and a client. And what happens here is that the server, our attack client is starting its clock, and it sends a message to our mock-up server. In this example, it says 1,000 nanoseconds. And the server reads that number, and it sleeps explicitly for 1,000 nanoseconds, and then it responds. And we can measure this time. And this corresponds to having a server which processed some data for 1,000 nanoseconds, and we still have the real jitter across the network added on top of that. And if you then repeat this experiment, for example, with 1,500 nanoseconds, then we can measure those two distributions, and we can see if we can distinguish the 1,000 nanoseconds from the 1,500 nanosecond distribution. And if we can tell you, okay, we can distinguish 500 nanosecond difference over this network link. So let's look at some of these. So this is a LAN with like a really pessimistic trial of having 1 millisecond difference. So these are obviously worlds apart, and you probably would only need like 10 measurements or something to make sure that these are different. But if you reduce the timing difference, we see that these are moving closer together. So this is 100 microseconds, this is 10 microseconds, and this is 5 microseconds. So still only using 1,000 repetitions on a LAN, 5 microseconds timing difference is pretty clearly separate, even with the naked eye, basically. If we go lower than this and we look at, in this case, 1 microsecond, this is kind of tough to see. So we increase the number of repetitions, and I don't know if the screen is good enough, but down here, you can, when you look up close, you can clearly see that the curves are still shifted. So with the box test here also tells us these are different. So 100,000 repetitions, 1 microsecond is not really a problem. And we hit the limit in our experiment, something around 100 nanoseconds is still possible. If you go below 100 nanoseconds, it's getting tougher. So sometimes we could still do it, sometimes we cannot. This may be due to all kinds of reasons. For example, the sleeping timer which we're using may not actually sleep exactly for the time we tell it to sleep, because it also relies on a finite resolution timer on the Linux kernel. There may be other reasons as well, but 100 nanoseconds or a little bit below is kind of our limit for this. Things look better if you just do a loopback attack. This was just for completeness purposes. If you run it on the same host against itself, you can get to 30 nanoseconds, and then below that, it's getting tough again. For the WAN, unfortunately, it's obviously not quite as good. Here we have 1 microsecond timing difference, which we can separate. But if you go lower than 1 microsecond, there's no way to separate the distributions anymore. We have some improvements for this, which I will talk about in the future work section, though. This is EC2. It looks very different. The bumps, we think they're coming from different other hosts running on the same physical machine. And they're really characteristic. If you run the same experiment a few times, it will always look the same. So maybe there's even opportunity for some fingerprinting there. But what you can see is still, when you zoom in a bit, these distributions are still shifted. I guess that's tough to see, but this is a 100 nanosecond timing difference, and the box test will be able to distinguish these. And it's interesting that Amazon has a really good network. It's as good as my cheap LAN switch at home, probably even better than that. So that worked really well. So in summary of this, we have loopback obviously is the best here, but if you have LAN and EC2 get down to about 100 nanoseconds, maybe you can do a bit better with additional improvements. On the WAN, we're limited somewhere between like a microsecond, definitely not 100 nanoseconds, but maybe somewhere in between there are still opportunities. So now you have all these numbers, but what does it all mean for your applications? How do you know how long like a string comparison takes on your computer if you're using your programming language, or how long does a SHA-1 computation take? So we try to put some of those things in perspective, and Joel will be talking about that next.
Thanks. Yeah, so let's look at a common class of timing side channels, one that probably a lot of you are familiar with, and that's string comparison. This was the first vulnerability that came to mind for me when I started thinking about timing attacks. And most string comparison functions return early. So they'll return when they see the first non-matching byte or sequence of bytes that are different between the two strings being compared. And this leaks information if you measure that, the time it takes to perform the comparison. So here we have an attacker interacting with a target, and the attacker is sending a credential over to the target, which is E9AA, and the target is comparing this to this sensitive credential E993. And we see over here on the left side that this comparison is actually happening 1 byte at a time. So when the target sees that the third byte is different, it immediately responds and says that the credential is invalid. Now the attacker can sample that interaction many times, send the same credential, and build up a histogram of timing measurements, and later the attacker can start trying other credentials. And let's say eventually the attacker tries a credential that where the third byte is actually correct. Then we see that the server takes a little bit longer to respond. It's responding at time t1, and this is telling the attacker something about the next byte of that credential. So these kinds of vulnerabilities are really easy to introduce. Anytime attacker-controlled data is being compared to some sensitive value on a server, and it's done using one of these naive string comparison functions, basically a comparison function that isn't written explicitly to take constant time, you have a side channel and a potential vulnerability. And these things pop up all over the place. So a lot of times you can take a code base and just grep for HMAC, and anywhere where HMACs are being handled by developers, let's say you have a server that takes a request and an HMAC from a client. It computes the expected HMAC value based on the request contents and compares it to the HMAC that the client sent along. If that comparison is done using your regular equality check in your language of choice, that's a side channel. And similarly with API keys, OAuth tokens, they're usually implemented as opaque blobs, sometimes using HMACs as well. And even authentication, if it's storing passwords insecurely, comparing them in memory, again, you have a side channel. And anytime you see this in a code base, it is an issue, especially with HMACs. It's undermining sort of the secure properties of that crypto primitive. So it's something you want to call out and something that should be fixed. But it's a separate question to kind of talk about how practical it is to exploit this timing difference remotely. And obviously the immediate question is, well, how much time does it take to compare one more byte of input? But there's another unstated assumption or often unstated assumption, and that is that comparison actually exits on the first non-matching byte of the input. But modern operating systems, 64-bit OSs, they actually compare entire 64-bit words at one time, atomically, using a single instruction. And this was pointed out by Nate Lawson back in 2010, back when he was doing these empirical studies. And it's really striking when you see it visualized. So, here we have the JVM. We're looking at Java string comparison. And what we've done is plotted the total execution time of a comparison as the index of the first non-matching byte increases. And what we see here is we have this like staircase graph. And the execution time doesn't change within word boundaries. The execution time is constant. And we're only seeing a bump in execution time when we pass that word boundary. So this makes an attacker's job really difficult because in order to see that timing bump and start to try to differentiate it remotely, they have to guess 64 bits of input. And that already is a pretty bad situation, regardless of what that timing difference is between those steps in the graph. If we look at an embedded system, this is a Beagle on Black running Linux. Again, this is Java string comparison, JVM for ARM. Surprisingly, this is using that naive comparison that exits on the first non-matching byte. So we see this smooth increase in execution time as the first non-matching index increases. And this makes an attacker's job easier. So this would be a system that would be potentially vulnerable. But there's still the open question of, well, how much longer does one additional byte being compared actually take? So what we did is we ran micro benchmarks. So what we're trying to do is isolate a basic operation in the system and get a sense of how much time it takes. And Nate Lawson, he did these measurements back in 2010 this was an Athlon X2, an early 64-bit CPU. And for C, Ruby, and Python, the numbers were looking quite bleak already because the time difference for one additional byte being compared is right around 1 nanosecond for C and Ruby, which is far from 30 nanoseconds over loopback or 100 nanoseconds on a LAN. Java, you're looking at 40 nanoseconds for a byte, and that would put it in reach. But on a modern system, like we saw the 64-bit comparisons, even with a timing difference like that, we're not going to get a lot of traction. On a modern system today, the situation has gotten even worse from an attacker's perspective. Comparisons in C are actually, this is less than a single clock cycle on the CPU that we were looking at, which is surprising until you realize that the i5 can actually run multiple instructions in a single clock cycle. And this is per word also. So these micro benchmarks, in addition to the fact that it's not using a naive comparison, really make these attacks impractical. But if we look at the embedded system, in particular for Java, which we saw earlier, we're looking at 18 nanoseconds for a single byte. Maybe if we try a few bytes at a time, we can get that time up, and this would potentially put it in reach of a remote timing attack. Things to bear in mind for this class of vulnerabilities, it looks like they're very hard to exploit in practice on modern systems. And now Daniel will talk about branching-based side channels with some positive results for an attacker.
All right. So these parts which Joel has been talking about is more about like a low-level primitive in your programming language or even CPU to perform these kind of operations. When I'm talking about branching-based side channels, what I mean by this is that there's like a high-level language decision or branching happening based on some sort of internal state or some information the system received and compares to something. Something that we talked about before about the username enumeration, for example. Is there a valid user, yes or no? And it takes two different code branches based on that decision. And the timing difference between these two branches obviously depends on the application and which kind of operations are happening along either of the branches. But if you can distinguish these two, then we can learn something about the system. So let's start with a simple example we talked about before, which is the user enumeration here. This is an experiment which does exactly that, the diagram I showed about the Ruby code earlier. Here we have, if a username is correct, the system will also perform a SHA-256 hash function operation. If the username is not correct, it will not do that. And it turns out you can distinguish that timing difference both on a LAN and on a wide area network between us and an internet host without really many problems. So this is something which you can distinguish. So obviously this is not an attack on SHA-256, it's just the way how it's being used, and that the execution time for it is long enough that we can actually distinguish this over the internet. So let's look at something a little bit more exciting. People are maybe familiar with what a padding oracle attack is, and I cannot go in all the details on how it's executed, but I'm going to tell you the prerequisite for it that we can figure out how you can mount such an attack. The idea here is that since AES is a block cipher, if you encrypt something under AES, the plaintext has to be a multiple of the block size. So if we have a shorter plaintext, we need to add some padding in the end to fill the block. And what happens is that the person sending the data is encrypting the data, sending it over, and the receiver is decrypting the data, and all implementations then typically check whether the padding was valid or not. If the padding was invalid, it would reject that and raise an exception or do something like this. And traditionally, the issue with this was that this exception of a wrong padding was disclosed to an attacker, and you could distinguish this from a valid padding, and this would allow you to mount a padding oracle attack. But even if you don't get information back, there is still a timing difference here which you can exploit. If you look at this here, we have an attacker sending a ciphertext to the server, and the server tries to decrypt the ciphertext. If the decryption has a wrong padding or fails in that sense, it will raise some sort of error and reject it. But if the data had a correct padding, the system will try to process that data. That can be anything. It can be just doing a database query to look up if that was an API token which was valid, or it could be some sort of parsing in XML or JSON or something like that. So something else will happen which will take more time, and we will have a different time T1 if that happens. So we can again distinguish these two cases. So just to show this, I built this little mock-up application which performs a SQLite database query. This is an in-memory SQLite database with only one entry, so it's a really, really fast query. And this happens only if the decryption was successful. So basically, we send in data, it decrypts the data. If the padding is incorrect, it returns an error. If the padding is correct, it will look it up in the database and then either return an error if it was found or if it wasn't. And here you see that there is a timing difference which you can exploit, and that you believe me that it actually works. I'm going to show you this in a little demo video. Right. So what we have here is like a server which we're taking on the left, is our mock-up server. On the right will be the attacker. And what's happening is that the attacker will send various different ciphertexts cycling through different bytes. And for some of those bytes, the server will take longer to respond because it does the database query. You sometimes see this flicking through on the left side. It's kind of too fast that my screen capture could get it. And whenever we get this, so this talk was given at Black Hat, that's why this video is still a bit outdated here. Whenever a byte was correctly identified as taking longer, we know one additional plaintext byte, and so we see the Hollywood-style decryption up here, where we uncover the secret one byte at a time. So you don't really see all too much, unfortunately, but the point is that at some points, the attacker attacked a longer timing delay than the other ones were, and at that point, it can infer that that byte had valid padding, and we can uncover the plaintext. So this is an actual attack which is using a timing side channel which can really do damage. I mean, if you can break a padding oracle attack like this, that's a big deal. And that's a good point which you can bring up if you're a consultant and somebody says, well, you cannot exploit this because we return the same error message in each case. That's a good way of telling them, well, you should still use an HMAC. All right, so some takeaways. First of all, we're not really surprised, but computing performance increases. And timing attacks are one of those weird things that usually when we get more computing power, our attacks are getting better. But for timing attacks, it's the opposite. If our computing power gets better, everything gets faster. Differences are smaller, and we can exploit it much, much harder. So since computers got faster, since like the last experiments people did, the chances of exploiting some of these vulnerabilities has gone down a lot. As you've seen, branching-based vulnerabilities are definitely something to look out for. They're definitely feasible in certain circumstances, but you may not always care. So it really depends on what the operation is, which you're making a decision on a branch to see if that's something you care about. Embedded systems, on the other hand, which we see a lot in the Internet of Things because we're sticking a chip in basically everything these days. Like, have you seen these egg trays, which are getting microcontrollers these days? So those ones are really a feasible target. And there's actually been a talk by Paul Macmillan at DEF CON and also next week at Echo Party again in Argentina, who showed using hardware timestamping and a direct cable connection to U light bulb controller, Philips U light bulb, that you could do a string comparison timing attack on that. And that's a 100 megahertz controller, so that's even like a factor 10 slower than what we were using with the BeagleBone Black, and that seems to be reasonable that you can pull it off with that. So just some brief words on how to prevent these. Well, if I'm telling you just make sure everything takes the same amount of time, that's probably not really helpful, but that's actually what people recommend. So I guess it's more like pick what you want to fix, what you care about, like with the branching-based vulnerabilities. I think both of us would say don't worry too much about string-based side channels unless you're using embedded systems. And if you want to see how you can prevent string-based timing flaws, there's our white paper, which I'm going to show you a link in a second, which has some sample codes on how to implement that for a variety of codes and languages. And then just completely outside the picture of your application, just make sure we need like 100,000 requests for some of those things. Just make sure your server doesn't allow somebody to flood you with so many requests and that you discover misbehaving clients and just lock them out, because that's just like a much easier way of defending a lot of this. And hopefully you're doing that anyways already. So in the future, we hope to have some more time to do some empirical studies and implement some of the attacks which are actually feasible. And something which we recently have started implementing, which is hopefully getting to GitHub very soon, is some interleaved testing. At the moment, we do all the long experiments first and then all the short experiments. But if you do this over the internet and your experiment takes 10, 15 minutes, then the jitter distribution over the internet will change. And if you look at the two distributions afterwards, they don't look very similar and it's hard to compare. So we want to interleave the short and long measurements and alternate them so that we have a closer distribution. And that's mostly done, but there's some few tweaks missing. So with that, the code is up on GitHub if you want to try it out, or email us if you have questions on how to get it running. On our company's website is a research white paper with more details about this and more background. And yeah, do you have any questions? Okay, I don't see the ones on this side.
Do you know why Java was so much longer than everything else in equals?
Was this in the 2010 measurements or the more modern measurements?
In both. The 2010 was like
The 2010, the difference there is really surprising. I don't really have a good explanation.
but you can realize it was so our was at 18 is that milliseconds?
Nanoseconds, yeah.
18 nanoseconds compared to like everything else, and that's crazy.
Yeah, I don't know. I mean, benchmarking is an art. It's easy to get it wrong, but
I think we're confident, though, that because Lake Northens also were much larger for Java, so we felt confident that that value is probably not completely off. And we ran it a bunch of times on different CPUs.
Yep.
And maybe Java does additional magic, or it does comparison, it does more Unicode comparison, while the other one is like byte comparison. That may be something which Java does. I don't know, just a guess.
Most of the actual objects used in Java, like string, the string class and all that stuff, is actually written in Java. It's just the
Yeah, it may be a larger amount of data being compared than just 1 byte in that case.
Here?
Yeah, go ahead.
For the branching test that you did, it seems like you did a test where you actually changed the flow of logic. So like test something, and if it fails, you exit out immediately, and if it doesn't fail, you do a large amount of work.
Right.
So what you end up measuring is you measure how long that work took. So have you looked at the cases where it's the only result of the branch is, say, like a pipeline stall? So the CPU didn't predict the branch properly, so the pipeline stalls and then continues on. And the amount of work doesn't really change very much. Is that something that's measured? Have you guys tried to measure it? And if you have tried to measure it, is it something that's even close to exploitable?
I don't know. I think my guess would be that it's not exploitable because the pipeline is only a few cycles long, right? And we've seen that we need like a lot of CPU cycles in order to have something which is exploitable. That would be my guess. I guess maybe on an embedded system you may have a chance again. Yeah, sorry, that's all I can say about that. Anyone else? No?
Any other questions?
If not, we're here tonight, so find us if you have questions, and thanks. Was good in time.
Yeah, we went over.